BC Chemistry, Unit 4, Interpreting a Low-Resolution Proton NMR. Okay. So, in proton NMR, we are basically looking for the number of peaks which correspond to the number of hydrogen environments in a molecule. And the area under the peaks normally giving us an indication of how many hydrogen are there in that environment. And in most cases, we are given the information of chemical shift. But although we are given that, it is also on our data book, but actually, in fact, we rarely use it. It is only until the last step when we have two competing molecular structures that we simply cannot determine without the chemical shift, then we go through the data book to have a look. Okay? So, HNMR step-by-step manual. Yes, ladies and gentlemen, it is chemistry for dummies time. Okay, so there are 4 steps basically. First of all, determine the molecular formula, which is normally given. And in fact, in most cases, a molecular formula needs to be given using a mass spec. And we'll talk about that later. Okay? And then write down all the possible structures for that particular molecular formula. Normally, when we reach HNMR, we would already know the functional groups that actually exist in that particular compound. That's why we introduced IR first. Okay? Then we use the HNMR to identify the number of hydrogen environments in that molecule. Last, we try to compare and find out for all the possible structures that we have written down in step 2, which one or which ones would satisfy the number of peaks actually on the spectrum. Okay. So, let's see. The question is that a molecule with a carbonyl functional group has a molecular formula of C3H6O. Its HNMR is given here. Can you determine the structure of this molecule? Well, step 1 is to determine the molecular formula. It's already given. Yay! And then step 2 is, what are the possible structures? What kind of structures we can write down based on the molecular formula and the functional group that already is given to us? Well, it has one unsaturation, and that's probably because of the carbonyl group. So based on the molecules and functions, it can only be these 2. It can either be a ketone or an aldehyde. I do not think you can write another kind of structure containing a carbonyl functional group, but sort of different from these 2. Okay? So, and then people ask, what if the question doesn't give us functional groups straight away? Well, actually, in most cases, the questions really don't give you the functional group straight away. That's why NMR needs to be combined with IR for analysis. So we introduced IR first. So normally we look at the IR first to identify the possible functional groups and or sometimes the combination of functional groups in that molecule. And based on that, we write down maybe 2 or maybe 5 possible structures. Then we use NMR to determine which one is more likely. So, step 3, use HNMR to identify the number of hydrogen environments. So this is the NMR spectrum, HNMR spectrum. Okay. TMS is the standard, it's the 0, so we don't have to count that peak in. Okay, that's just the reference. And then besides that TMS, we only have 1 peak. That means in that molecule, there is only 1 hydrogen environment. Then for the 2 structures we have written out, which molecule only has 1 hydrogen environment? This is step 4. Okay? A aldehyde, no, it's actually 1, 2, 3 different hydrogen environments. 3 different hydrogen environments should produce 3 different peaks on the spec. But since we only have 1 hydrogen peak on the spec, that cannot be it. So what if the ketones then? Well, we talked about this ketone before. It has all 6 hydrogens are in an equivalent position. They are all connected to the carbon that's next to a carbonyl group. Although they are connected to 2 carbons, but these 2 carbons are also in the same environment actually. So all 6 hydrogens are in the same environment. So the winner is our ketone. Area under the peak. So sometimes when the peak is really narrow, that looks a lot more like the height of the peak, but it's actually a small area under the peak. So the area indicates the number of hydrogen in that particular environment. So as you see, you can probably guess, the higher the peak, the more hydrogen in that environment. So for example, in this case, we have a compound that looks somewhat like this. It has 2 hydrogen environments, which means that it will produce 2 peaks. Because it's a symmetrical compound, so these 2 carbons connected to the 3 hydrogens, altogether 6 of them are in the same environment. Okay? And the 2 hydrogens in the middle is in a different environment. So since 2 are in the one environment and 6 in the other, so the area, or more likely for us to see, it's more of like the peak, indicates there are more hydrogens in this environment and less hydrogens in the other environment. However, it is harder for us to actually use the area under the peak to deduce what molecular structure it is. But the height actually will help us to confirm our deduction. So once we've written out and we've concluded this is the molecule that corresponds to that particular NMR spec, we can then use the height of the proton NMR to help us to confirm, or does it actually correspond to the number of hydrogens in each environment. Especially sometimes we are given the ratios, so we can actually confirm it using the ratios given.